Okay, so welcome everyone to the first webinar, the first PICUP webinar in the series of Fall 2024 and Spring 2025. First disclose information is that, as you can tell, my voice is not the best right now, which is okay because who doesn't get a cold during the fall time, right? So that should be okay. I see people joining the session, which is very nice. It'll be very nice if possible, if people can show their face. Otherwise, it's okay to see your names and the picture. But in general, thank you very much. Just kind of for the sense of community, it's nice to see our faces. I'm very excited to introduce to our speaker of today, Viviana Acquaviva, who is a professor of physics at City University of New York. Today is the first time I'm talking in person with Viviana, but I know a lot about her because in social media I saw a year ago, more than a year ago, when a textbook came out on how to teach machine learning. And when I saw the book, I was super excited. I said, I have to get that book and I have to talk to her. And I'm very glad this is the opportunity to learn from Viviana. So with that very non-official introduction, it is your turn, Viviana.
Thank you. Thank you so much, Patricia. It's really a pleasure to be here and to meet, at least virtually, so many of you. I'm really glad to see that, we can have this kind of crowd for something that happens after work. So, like really impressed, and I hope I won't make you regret it. And it's lovely to hear, to sort of, join a network of colleagues that maybe are thinking about similar things and challenges. And so what I'm hoping to do today is really to have a conversation. I have prepared some materials, to tell you a bit about what my experience in teaching machine learning to physicists has been, tell you a little bit about the book and some other things that I have put together. But, I feel like I still have a lot of struggles. And so, I'm hoping to, take not a lot of your time with my blurb and to turn it into something which is more interactive, where maybe we can discuss, like what, your experience has been, what kind of challenges you are encountering. And also I'm going to, go ahead and talk through some slides now, but I'm happy if you can, feel free to interrupt me at any time. I think, I don't have an agenda. I don't need to get through everything. So if we just turn this into a conversation, I'm very happy. Let's see. Dun, dun, dun. This is like the obligatory. Can you see my screen? Okay. All right. And as Patricia mentioned, I'm located in New York. My main institution is CUNY, and here is my email. So if you want to reach out to me at any time, please feel free to do so. So I'll tell you a few more words about me and what I do and what my path has been, especially because it's a little bit unusual. So CUNY, City University of New York, is the biggest urban university in the Northeast. We have 250,000 students, so at least that was the number pre-pandemic, but now it's possibly a little bit lower. But basically, there are 24 senior colleges that are spread all over the 5 boroughs of New York. And so City Tech is mine. It's one of them. And then we have one graduate center, which is the umbrella for all the graduate programs. So it's, it's kind of like it's a different place than many others. And so our student population also, as a consequence, I think, has peculiarities and, for us, understanding how to best serve them is always something that is on our mind. I come from a place in Italy called Lecce. It's in the heel of the boot. It's known for its beautiful architecture, sometimes known as the Florence of the South, beautiful beaches, great food. I won't tell you anything else because, it's 7 p.m. Of course, I haven't had dinner, so I'll stop here. I'm a reformed astrophysicist. For many years, I had this on the slides as an improbable astrophysicist, and now I have to say that, I have officially sort of left the ranks. And as of last year, I have sort of formally changed my area of research from astrophysics to climate science. And in general, AI has been like a big part of this transition, but in a way that's been what has been stable over the years. So, I'm happy to also talk about, my career change and, how it happened, but this is not the main topic for us. And I'm a mom to this young lady called Clara, she's 8.5, and she is in 3rd grade. Also a big part of my life. I'll tell you a little bit about what I have worked on and what I'm working on now, just to give you, a sense of what my interests have been. I started actually on a very theoretical path. This was, we're talking about 2003, so a long time ago. My first papers were around non-Gaussianity from inflation and like lots of pen and paper calculations. And I work a little bit on gravity. I think this is, let's say, maybe like late PhD years. I started to work more in numerical cosmology. And I realized that, I really like methods. And so I work with statistical tool and inference tools from there. Then I moved for my second postdocs to spectral energy distribution fitting of galaxies. And then this is like circa 2014. This is where I started to be a bit more serious about machine learning. One of the reasons for that is that I wanted to leave academia. I was already on tenure track, but I was like bored to death and looking for something new. And so I was like, okay, I'm just going to learn this stuff so I can go and find another job. And instead, the effect was that it rejuvenated my love for research and I think that I could do and the students I could advise. So I think that sort of in the end, it turned into a motivation to stay. And then I work on deriving galaxy properties from large simulations and also, thinking about how do you validate large cosmological simulations in the sense of, like, for example, if we are using some of these statistics or machine learning tools to learn from simulations, how do you build trust in these models? And how do you use them to maybe find ideas for physical models of galaxy evolution? And then, as I was saying, as of last year, you can see another pretty big change. This is sort of like my periodic 10 years crisis. So, last time I was like, okay, let's learn machine learning. This time it's like, let's move to climate science. And so these are things that I'm thinking about now. One of my direction is actually how to develop metrics to evaluate the outputs of global climate models, which is actually not that different from what I was doing before with cosmological simulations, just different data. Another direction that I have is reconstructed the ocean carbon dioxide fill to understand the ocean carbon cycles. And this is a problem where you have data that are sparse and biased both in space and time, and you need to fill in both directions. And I'm also thinking about, in general, like ethics and reproducibility and what open science means once, AI enters the picture, in particular in climate science. Okay, now on to two more topical things for today. Why did I start thinking about teaching machine learning to physicists? I have to say that, this was something that I used to had to justify more. And now I feel like, okay, everybody believes it. So it's less controversial than it used to be. So this used to be my graph that I update every couple of years, just looking on the ADS, astro, and physics papers and looking for papers that have machine learning in the abstract. You can see that this is a pretty neat exponential curve. Right? So I feel like this is something that is happening in the community. And so I think, making more people able to follow and to understand and review and critique these papers is important. But I feel like, from the perspective of undergraduate students, because this is where we started, we developed a major in applied computational physics. with the idea of having something that is a bit more practical and maybe directed to students who are not just looking to grad school as a career opportunity, but who actually need to find a job after they're done with college. And so we do things like computation methods and quantum computing. We also put machine learning in the picture. And our idea was that, maybe there are good opportunities for social mobility and, just finding interesting career paths if students get this type of education of, this type of skills at the college level. And then actually, as we know, I think it's basically impossible to do anything without hearing about AI these days. And so the way I think about it now is even more fundamental. I just feel that, I used to think about something that was splitting the scientific community, right? Whether or not people could follow up about machine learning and AI. But now I really think that has become a more societal issue. And I feel like everyone in every major, at every stage should have some understanding of what these methods are, what's the philosophy behind them, what are the things that we should be scared about, or, or at least, being able to make a decision about, what we're scared about. So I think it's important. Let's see. So when I first, we started this major, right? I don't know if you had this experience, but when we started this major, it was a major that we had tried. I arrived at the college in 2012, right? And there was always this proposal for a physics major that never went through. And then we decided to give this sort of like applied and computational angle. And it was approved within 6 months, which was great. Right. And my colleagues were like, you wouldn't believe how long it's taken us. And I was like, well, I guess that you had to find something that makes it a bit different. But, the moral of the story was that we found ourselves with all these new classes to teach and, very little lead time. So for me, I had, we ran the machine learning class, I think in fall 2017 for the first time. And, I had put together like a course proposal, but I didn't have anything else. And so I looked around to see, okay, what kind of things can I use? And these were the 3 books that more or less saved my life. However, I think what I found that my needs that were not met at the time were that I needed material that was accessible. So at the undergrad level and without too much math. This is also something that in general, as much as I love math, I think that sometimes it can be an intimidating language. And so, in general, the approach that I have to machine learning is very, very practical. And I didn't find a lot of material at that level. I wanted problems that were domain specific because I feel like, of course, there were a ton of things in computer science, but I do think that the way we use problem solving in the sciences is different. And so we are trying to find insights. We are not usually trying to build a system or an architecture. And so I found that a lot of the problems that I could find in existing tools were just not relatable for me. And I couldn't really use them to, try to teach students how to think as a scientist and have that thought process. And then also, again, this is more like a nuanced thing of, I could find a lot of intro materials, like, what we call 101 data sets that are so curated that basically these are data without any outliers, without any missing data, without anything interesting or, real world like. But then, the alternative was go somewhere and download this giant raw data set that then, in which case you need so much pre-processing before you can even start thinking about, how do I solve this problem? That was too much. So I was trying to strike some balance there. And so this is, I'm still not very sure how, but turns out I ended up writing this book. So of course, it's not that I went directly to writing the book. I, first taught the class a few times. So I had a bunch of materials that I had largely put together on my own. And then somebody asked me, what book are you using? And I said, oh, I don't have a book, but, perhaps I'll put something online. And then I had the sabbatical coming up. And then I had the naivete of thinking that 1 year would be enough because I already had all the materials. So just don't do like me. if somebody, suggests that you should write a book, unless this has been, one of your life dreams, just don't do it. However, after the fact, we can now talk about it. So I'm, in the end, I guess in retrospect, now I'm happy that I did it. And so this is the book that Patricia mentioned. It's called Machine Learning for Physics and Astronomy. And it's meant to be like a very practical guide to, like learning the basics, the foundation of algorithms, of evaluations, of data processing, with the idea of physical sciences and astronomy in mind. So I wanted to show you a few things. One is the fact that we try to keep the price reasonable, but also if you subscribe and if you're willing to get email from Princeton University Press, at any time you can get a 30% discount. So I think this is nice. And if you're actually an instructor and you're curious about it, you can do this request exam copy and you get a copy for free. So this is, I think, something that could be useful if you're curious, right? You can do it at any time and you will get a copy and then you can decide if it's something that is useful for you. I want to spend a couple of minutes on these two links. I don't know why they put them so tiny. So one is look inside, that, so we can look at the table of contents just so you get an idea what's there. The other one is these resources. I will refrain from praise. Imagine if I, click there and then it's empty. So let's just do the look inside instead. And so for this, I believe that I need to change which screen I share. Okay. Okay, so this is the cover of the book and this is the table of contents. So I would say that this is largely an upper undergraduate level. This is what I was striving for. I use it to teach both undergrad and graduate classes. So we can talk later about the difference. So there's some introductions to machine learning method in general and jargon, nomenclature. We start from supervised learning with simple things like k-nearest neighbors and decision trees. I'd spend a good amount of time on evaluation and diagnostics because I think, again, this is something that you don't often see a lot of detail in other textbooks, but I feel like that in science, deciding what thing is important to you, what is the thing that you're actually trying to minimize or maximize is a big question. And so just, like thinking around model evaluation, I think is very important. And then also just, how do you diagnose how your algorithm is doing, both because you want to improve it, but also as a way of making more interpretable, right? And so sort of like generate, you don't want something that is a black box, right? So I think this is a way of making it more, opening it up and make it more interpretable. And you can see that basically at the end of each chapter, there are these review and discussion questions. So then I used, for assessment or for discussion, and then there are some programming exercises, and these are in Python. Actually, the programming exercises, this is just, something that they're asked to do. But then, the worksheet that are connected with the book or the solutions are in Python. And we talk about optimizing models. We switch to regression. We have ensemble methods, things like, random forest and XGBoost, which often without going to neural networks are the most powerful things that you can do. There's a little bit, not enough, sadly, about clustering and dimensionality reduction. This is just because there are only few simple things that you can do. And so this is all I could include. A tiny bit about neural networks. This was, like one of my first choices was that writing a book about deep learning means that your book is obsolete within 2 years. And in fact, I do think that this is this beyond fully connected networks and after, this is the only part that is probably thoroughly useless at this time because the methods that were state of the art 4 or 5 years ago when I wrote this for the first time, and even when I updated it, are now so different. So, like we had GANs, we had, encoders, I guess they have somehow survived. We had convolutional neural network, we have recurrent neural networks, but, there is nothing about transformers. And I bet that, in 4 or 5 years, the architectures that are most used will be different. And then I think this is a nice chapter. This is something I added after the reviewers came back with ideas, which is sort of like a short summary of what to do when you have a problem, you have some data, then you sort of like want to make a pipeline of what to do next. So I don't want to spend a lot of time now, but this is something maybe we can come back to if you're looking for, if I only look at one thing, what do I look at? I think this should be the thing to look at. Let's see, another thing that I wanted to show you from the book website was this resources tab. Can you see it? Something very tiny that says instructor resources and student resources. Okay, so if you click on instructor resources, you will have to provide, request access and basically prove that you are an instructor. And you get a set of slides for every chapter, notebooks, which are Jupyter notebooks with, worksheets basically and data sets, so work examples, and then also some sample assignments and solutions. However, even if you don't want to go through this process and you instead, sorry, I have lost my tab, forgive me. Even if you click on student resources, I'm not gonna click because then I would download the notebooks and slides for like the millionth time, but basically these are identical. So, if you don't, if you're not immediately interested in assignments, which is actually a small collection, this is another way that you can, just look at what materials are available and decide if they could be useful to you. So they are, available for everybody. It has like data and worksheets and it has slides. So far, so good. Do you have any questions or comments before I continue? Yeah.
I'm sorry. I joined a little late. I'm sorry about that. I have a quick question. So how do so if I request exam copy to Princeton University Press, then they will send me a copy?
Yeah.
Okay. Thank you.
Well, hi, I have another question. So you mentioned that the book was meant to upper undergraduates, but you also use it for graduates. Is that mostly related to the content of machine learning or also to the content of physics and astrophysics? In other words, how much physics and astrophysics do you?
Oh,
Yes.
do they need to know?
Yeah, like for example, if I was thinking actually of adopting your book for a sophomore course that we have in our sequence. So will that be too early? What kind of physics?
No, they don't need any physics, not even calculus. I would say the linear algebra is probably the biggest thing that they need to know. I usually, for my class, even in Astro, I do require Calc 1, not so much because there is not a lot of calculus, but the idea of optimizing functions to be there and solid. And I think just, some exposure to abstract reasoning, I think is very important. But in terms of, like prerequisite knowledge, I don't. In fact, in grad class, it's not just physicists. I have people from biology. I have people. So it's more like sort of some, habit of thinking about, critical thinking, mathematical thinking. So I think they should be comfortable.
Well, right. Thank you.
Of course.
I have a question in the same line that Raul Morales. For example, in the book, I feel really interested in this book, Machine Learning for Physics and Astronomy. And I want to know if in each unit, for example, here, if you explain how these tools of machine learning is used in this physics and astronomy. For example, some work for final of this topic, or how you introduce these topics and combine the machine learning with the area.
Okay. Yeah, I think this is a very good question. I think, let me actually show you. I don't even have a PDF copy of the book because even the electronic copy, like even for me, I have to go in the sort of like e-reader format. But if you guys don't mind, I will show you the, I guess that the best proxy I have to a PDF copy is like the proofs. But maybe I can show you exactly how the beginning of one chapter looks like, and that hopefully helps with these questions.
Okay.
So what do I want to do? 1 second. Or maybe it's here. Oh, no. Sorry, I have several things in my computer that are making things a bit difficult to see. And then from here, I want to say chapter 4. Okay, let's start here. Okay, can you see this?
Yes.
Okay, so let's say that this is like chapter 4, we do optimization here. And so in this one, I have a problem that comes from the standard model of particle physics. So this is a simulation. So actually a colleague who is in particle physics in the Netherlands gave me. This was something that he was using in his own actually more advanced class. And this is some simulations of what happens in proton-proton collisions at the LHC and looking for physics beyond the standard model. So of course there are, like many possible channels of particle decays. The one that we were looking at is basically if you can distinguish between 4 top quarks or a top and a top bar and a TT bar, because I guess the relative abundance of this can be a sign of physics beyond the standard model. So what I do here, and the algorithm that I'm introducing in this chapter is support vector machines. So what I do here is like, I start with a description of the data set. And this is, I think, is like fairly similar to what I do in other chapters. And so I try to give them a bit of a background about, hey, this is the standard model of elementary particles. And this is, how we have the ones that we believe exist, how we have completed it with the gauge bosons, and then how the Higgs sort of is able to solve this problem that different gauge particles have different mass, which is something that was puzzling for a long time. And so these are just like the basics, right? So let's say even someone who hasn't seen particle physics before certainly won't become an expert, but at least will be able to understand the jargon that is used there. And then, so we describe why we have a necessity of physics beyond the standard model. Well, a necessity, I don't know, perhaps it's too strong of a word, but why we're curious about physics beyond the standard model. And then, I think this acts as an introduction to the data that we have. We describe now, like the particular decay that we are looking at and what kind of particles are produced. And so this is, and finally we get to the data set description, right? So let's say we have 5,000 examples that were selected at random from a larger data set. And of course the data is available, right? So then, you will go in the notebooks and you will find the exercise and you will find the data set. And then we describe what we know about the different particles. And this is the format of the information that we have for each event. Now, so we have the missing energy expressed in these particular coordinates. And then for each particle that has been produced, we have a quadrimomentum. So this is, let's say, the part about the data. And then I describe this algorithm here. And so, this sort of goes to the other side. How do support vector machines work? And so we start from, how we can build linear separators between different classes of data. And then what happens, this is actually one of the highest mathematic things with, just a tiny bit of, well, a dot product is not so bad. I'm just so used to, trying to simplify things, but I guess that, the equation of a line and understanding that, if you're on different side of the line, then this quantity may have a different sign, it's okay. And so how we can describe this problem as a constraint optimization problem. Then what happens when we have data sets that are not exactly separable, but but they can if we give a penalty to the mistakes that we make. And then there's a concept of kernel functions, and And then, I talk about what are the hyperparameters, the things that you can tune about these algorithms, and try to give some examples, right? So this is, for example, for different values of the hyperparameters for the same data, how the boundary found by this algorithm changes. And then I guess this is where we try to put it together. So the first part here is data exploration and pre-processing. This, in a way, is not sensitive, right, to the algorithm itself, but these are just, things that we need to do, right, when we are looking at the data set. This is an interesting problem because there's a different amount of features that we have for each examples, because different numbers of particles are produced in each event. So you have a big problem about, what do you do about the data that are missing? So, we talk a little bit about imputing. And then, and you can see that this is, shows you little pieces of code. Actually, in the actual book, this looks better. In the proof, these are not the best looking. And, we talk about, okay, what are our expectations? How do we benchmark? And then what happens when we start building models. And so in the book, you also will see, like a little bit of text and then a little bit of code. And then, remember the previous chapter was about diagnosing the models. So this is something we pick up here. So sorry, this was like a very long answer, but I figured that maybe it was useful to just show very practically how does this look like, what kind of narrative would you be reading? And so on. And then actually in this chapter, this is, I promise is the last thing that I say about this, is that the best, this is the best improvement that you can get is through feature engineering. And so for this, I actually had to go to my particle physics colleagues and say, okay, I think I'm stuck, like I hit a wall. What I can do from the machine learning perspective in optimizing these models is done. Can you talk with me and tell me about some variables that perhaps I can build based on, how you understand these collisions that could help. And we show here that this is actually like the biggest help that we can get. So yeah, so I'm trying, to put together different sides to show that sometimes you get help from the algorithm perspective, but a lot of times you actually get help from the domain knowledge. Was that helpful, at least, despite the many words? Okay.
Thank you so much.
Of course. All right, I will. Thank you. I see someone say, love the opening jokes. Every chapter has an opening joke that is by me, and this is probably the part that I'm proudest of. So thank you for noticing. Where am I? Here. Okay, so I wanted to show you what I do in my class in practice. This is a class that I've now been teaching for a few times, although things have changed. So this is my current syllabus for my undergrad class. I usually start with a few weeks of recap of like basic statistics. There's another things, they don't need much, but they need to understand a distribution and what are the different properties of the distributions and what is a random variable and, what it means to be deterministic or stochastic. So I found that the easiest thing for me is to just do a review. Like I used to try and give them reading materials, but I think, in the end, there's so few concepts that I've just, created a class. And same thing for programming. One of the challenges I have, which I'm not sure if it's relevant for you guys, is the fact that students come in with with a very big range of abilities in programming and previous exposure to Python or Python for problem solving. So I haven't found, just maybe because of what's offered at our college, a prerequisite is not the obvious answers. Also now we have put a course of methods of scientific research, which is in Python, which we're hoping will help. But in general, I spent a couple of weeks just doing a review. And this year, I just decided to embrace the chatbots. And so I also have a guest lecture on GitHub Copilot, because I figured that, it's better to show them how to use these tools properly and then, have rules, as I will discuss later. And then, at least with the undergrads, usually start from, introductory concept, and more or less we go through all the topics that I showed you, so all the 8 chapters. I do a lot of in-class assessments. I'll discuss why in a moment. So I have about 8 of them that are 30, 40 minutes. And then I do a final projects, both with the undergrads and the graduate students. For the undergrads, I give them a choice. I prepare the data. I give them the choice of a couple of things that they can choose. And their goal is to build a predictive model, maybe beat a benchmark, but mostly just to, wrap their head around, what they need to do to go from a problem to a proposed solution and what that process looks like. So we tend to just do that for the last couple of weeks. So in each class, usually there's me lecturing on something. I don't know, this is just a slide on gradient descent, but this also gives you an idea of how the slides look like. Again, I think very simple. And some notebook work. So I'm trying to show them the things that we are discussing in a slide in a practical example. So I'll show this next. And then I have these review quizzes or assessment. So this is an example of questions that I could ask when we're talking about linear regression. We talk about the normal equation, which is the analytical solution for mean square error loss. We talk about batch gradient descent, which is just normal gradient descent. I don't even know why they call it batch. There is no batch. And then stochastic gradient descent and mini batch gradient descent. And so we try to, for me, something that I try to do very hard is to help them develop some insights about when you should use a certain method and why. And so this is, in this case, I'm asking them, okay, if you have, for example, a few objects in your data set, but a large number of features, which of this method would you not use? And in this case, the answer would be the normal equation because, there is a matrix inversion and the matrix is M by M, where M is the number of features. And so the computational scaling of this is pretty poor. So this is something that we discuss in class at length. Why do you need this when you have an analytic solution? Why would you use a numerical method? So I think this is something that for me, it's important that they remember. And I guess this is an example of notebook. So what I do, I'll show you actually in visual code, is I now upload 2 versions of the notebooks. One is pre-class and the other is post-class. And so in the pre-class, basically, I try to leave some little bits that need to be filled so that we do it together. Let me see if I can share the actual code. Yeah. Right, so this is an example how this would work for gradient descent. Right, gradient descent is such a fundamental idea and also very easy to code, at least, if you're not fancy. So I feel like it's something that I want to show them. And so this is what I uploaded pre-class. I'm not going to run it, but this is how the typical notebooks that you will see look like. So they have code, but they are pretty extensively commented. So we pick the model, and then, this is how we generate the data, and we will plot them and blah, blah, blah. And so this is how we add the bias here. So this is, what I'm calling unfilled. It's not a lot. So here I'm just asking to say, okay, this parameter M that, then will go in your calculation of gradients and in your step update. What is it? And, they just have to figure out, okay, look, it's just a number of data points that I have. And then, when we are together, we have maybe just, in the slides, we have seen the fact that, for mean square error loss, you actually have an analytical expression for the gradients. And so we put it in here together. And then we understand that, updating your location in the parameter space, it's literally just, taking some step size that is here and multiplying, and taking a step of that size in the direction of the negative gradient. So, after the fact, this is how this code looks like. And then, of course, we do things like plotting the paths and and things like that, and maybe comparing the path of the different algorithms like batch gradient descent, which is deterministic, so it's this one, stochastic gradient descent, which goes all over the place, and mini batch, which is sort of like in between the two. So this is just to give you a sense of, what you will find in those notebooks, how those look like. Sorry for the back and forth. Was I here? Okay, perhaps the last thing I wanted to discuss is how to do assessment. And this is something where I really find myself at a loss after, this is the first semester I teach fully post ChatGPT. And so I used to give a lot of worksheets take home and to just use the review quizzes in class for like extra credit. I would ask them to work in groups and just find the answer. And I love that activity. But now I basically feel that I want them to learn how to use AI, but I don't want to spend my time figuring out whether or not they have used AI in a way that I didn't approve of. It's just something that is so, it's just like a horrible way of spending time. And so basically, I feel like for me, this means that I don't know of ways to assess whether they can write and understand code, which is a take-home work. Even for more theoretical things, this is something that it's now very easy to find solution to. So I do this 18-class assessment, and I actually have to, I also want to do coding assessment, which is interesting. So this is an example, for example, how I test coding with pen and paper. So, this is an example of what they had a few weeks ago. I tell them, okay, this is a line of code. What type of data structure is the one that you just created? Or, they have to write down little pieces of code, right? You want to define this with the first 5 columns of data. What line would you write? Or, they have to complete. This is something that they also like. Maybe I ask them to comment each line, just so they can understand what is happening. And they can use all the worksheets. I let them print them, right? In a way, it's not that, because in real life, it's okay. You can actually run the cell and you will get an error. But for me, it's just like a way of saying, okay, do you understand what these things mean? And I'm still struggling. I had to redo all my assessment this semester. So if you have better ideas, I would love to hear. In graduate classes, what do? I have a mix of students, which I really enjoy. So I don't do my Python review. Some of the questions that I ask or the homework are a bit more complex, of course. For example, I could ask them to write pseudocode for specific algorithm. Just, there are many algorithms in which really you just need to write a sequence of operations, a very good exercise. Although again, now there are such easy ways of doing it that I'm not sure I can do this anymore. We do a bit more deep learning. And so in New York, that's a nice thing, is that we have so many experts in the area that I can always call in guest lecturers. But in 2023, which is the last time I taught this class, I will teach it again in the spring, their favorite topic was AI ethics. And this was actually something that was really nice and surprising for me. I thought they would be, wanted to hear about transformers or, maybe some other of the newer architectures. And then I asked them for a self-directed final project. So they have to come up with a project. It needs to come from their own research interests. And for a lot of them, if they haven't used any machine learning, it means that they have to come up with something that is relevant for the research field they have chosen, where they can use ML. They have to provide the data, and they have to sort of write a pipeline of what they will do. And I help a lot, especially because usually they come with something that is very unrealistic. So, a lot of my work here to actually, tone it down and say, okay, have you thought about where you will download the data and how big they will be? And, if there is anything that you need to do, but actually works quite well, right? Just because we have this big range. So I found that what tends to work is to mix and match, to reflect on when algorithms are useful and why. So this is something that I spend a lot of time thinking about. Do you expect that this algorithm will work here? Why? Why not? What is, they want to know, okay, what is the accuracy that, is 80% good? And I'm like, I don't know, what do you think? How can we figure out if 80% is good? The way of where we can embed domain knowledge in pipelines, for example, through feature engineering, is something I find is very important for these classes. And in graduate classes, I try to discuss things that are a bit more advanced, for example, uncertainty estimations or imputing early on, so that we get more practice. And also I discuss how we can develop custom metrics, right? Because a lot of times what we want to do in science is not just find the highest accuracy. What I'm struggling with is that the coding part is not interactive enough. Even these things where I show you, okay, we fill these things together, I feel like it's not enough. We will need a lot more practice in class, where maybe they have to fill in bigger chunks. But I found it difficult because, one, I don't have time. Two, I have like a huge range of experiences, and I'm not sure how to cater to them. And also, not every one of my students has a reliable laptop to work on. So maybe at home it's easier, but something that they can bring to class, not necessarily. And so I find it hard to engage everyone. I really loved having the review quizzes, not for grade, because then I could ask them to, talk in groups and tell me. And so, I'm struggling with how, the assessment part. So, if you have found something that works, I would love to hear. I also wanted to mention 2 other resources that we have created. Together with 2 of my previous students, we created this free massive online open course, which is on the Flatiron CCA website. It's like it was sponsored by the Flatiron Institute. And so this follows the book really closely. It's available to anyone. So they can actually, maybe I can show you. No. So I just need a browser, and here. This is how the course looks like. And so, this is very similar. So we have video lessons that I have recorded. Oh, sorry, I'm just noticing now. I don't know if I'm in the Spanish side. No, sorry, we did a few things. I don't know why now they have the subtitles in Spanish instead of in English. Oh, well, I guess I just discovered something we have to fix. We just put online the Spanish website. And so I think maybe we have some crosstalk that shouldn't have been there. But, we have like, video lessons for all of these. And then we have, let's see, for every chapter, we have quizzes that anybody who's taking the course can take. Okay, and so this is how they look like. And they're similar to the ones in the book, but now there is like a live version. And so this is something that anybody can use, either to maybe watch a lesson instead of reading, or maybe, try out their understanding with something like this. And again, as I mentioned, we just, together with this group of folks coming from different countries in Central and South America, we just completed the Spanish version. It's called Aprendizaje Automático para Física y Astronomía. And I really wanted them to re-record all the videos. In reality, we had to settle with the translation, but all the materials are in Spanish. The notebooks are in Spanish. All the comments are in Spanish. The quizzes are in Spanish. They have a glossary of terms. So we're really hoping that this will be something that, maybe makes these topics more accessible to a bigger community. And as I said, both of them are free to join. And I think this is all on my side. I apologize. I had planned to spend more time, but I always talk more than I should. But I'm happy to discuss anything that is on your mind or hear what you may want to say from your experience.
Well, thank you, Viviana, for this presentation. I'm clapping on behalf of everyone.
Thank you, Patricia.
I wondered if Nick is around, but probably I wonder if the audience has questions. I will invite you to unmute yourself and pose the question, please.
So you mentioned that the take-home worksheets are now more suffering from the like unwanted use of like ChatGPT or something like that. So how did you change that activity, or how did you like modify that activity so that there will be like more learning, less academic integrity violation, or those kind of things? Thank you.
Well, so exactly. So basically, I do a lot of assessment that are in class, and they're pen and paper. And then on the worksheets, there's only 3 and the final project. And for this, I have shown them how to use it. And they are allowed to use everything because I feel like that's also useful exercise as long as they disclose it. So the thing is that this has taken away a lot of exercises that I used to have, but I haven't found a better way. I basically feel like that I cannot say, do this at home and don't use ChatGPT. So I went for embracing it for the take home and just do more assessment in class.
Thank you.
Of course.
I have a question, Viviana.
Please.
For example, for pre-graduated course, maybe in physics, what course are mandatory before take this course of machine learning for physics, science? For example, what course you recommend that a student take before take this topic or this subject of machine learning for physics?
Yeah, this is a great question. We're still struggling. We didn't find the perfect set of prerequisites, but I think the things that are most useful are linear algebra for sure. Like I think, they need to understand matrix multiplications and, to be comfortable with that. I think calculus 1 is also a good one just because, thinking about functions and studying functions and behavior and gradients, I think these are things that are also important. And some programming. So what we did is to create a course called Methods of Scientific Research, where we do simple things like fitting a line, like simple inference, a little bit of MCMC, and we do this in Python because I feel like this is really what's needed, some sort of like habit of solving problems with code and a sort of like, comfort with describing problems in that framework. But I would say at the very minimum, I think linear algebra, maybe Calc 1.
Okay. Thank you so much, Viviana.
Of course.
I see a question on the chat. Ernie, I believe, posed the question.
Yeah, so yes, it does mean the ethical use of AI. And this is also something that I started working on as a consequence of that with the person who gets lectured. So I think basically it was a reflection about how we can frame ethical questions that are very complex in the language of understanding AI as a system or an infrastructure. And so for us, this means, or this has meant, for example, let's say we're writing a paper. Like, what does it mean to be ethical? Maybe we don't think like that, okay, a physics paper is going to have like these incredible consequences for the world, right? However, our algorithms have biases. Maybe and now that I work in climate, actually, this is more relevant perhaps than when I was in astronomy. Perhaps the way that we are that the data will be used is not the intended use. And so maybe, like being very clear about what is the domain of applicability, understanding what are the failure modes of our system is another way to, protecting others from unfair uses. So basically what we've been reflecting on, and what I in particular have been reflecting on, has been, what it means in practice, in our scientific practice, to make more ethical choices. So not so much, I feel like the big picture of like what's ethic is too broad, is so intimidating. But I want to think about, how can I make the results of what I have as clear as possible for the biggest audience, and to also, like take the time to explain, look, you shouldn't believe this model if it's applied to this other field, or, like it's, this is where I expect my model will break down.
Thank you. I think it's really, it's timely to think about these things because the American Physical Society is revising its code of ethics right now and soliciting input from members. Also, the AAPT is the American Association of Physics Teachers is beginning to consider putting together a statement on the use of AI for students. Just because I think we need to attend to these issues. You can't ignore it, right?
No, absolutely. Even the fact that journals don't have clear guidelines, I find it puzzling. I understand that this happened fast, but I don't know how you feel, but in reviews and things like this, I feel like we need the rules.
Viviana, I believe there was a previous question on the chat asking a question posed by Stuart Crawford.
Okay.
He was asking, how large are your classes?
Yeah, very good. I capped them at 15, so I'm very lucky. And I feel like in the undergrads, because the assignments are relatively simple, I think I could take a few more, but I don't have TAs. And I feel like in the grad course, because they have essentially 15 different final projects, I just feel like I can't handle more. So, one could have bigger classes, of course, but I think then the assessment part, at least, we need to change and rely more on maybe like the one in class or the programming. Yeah, having group stage or quiz work. And let's see, I have another question, no?
I see a question by David Chappell.
So, do you use or know of any repository for scientific data sets for machine learning projects? Yeah, this is a great question. In my original ambitious plan, I wanted to create one of these as part of the book. And in the end, I didn't. However, I will say that I think I have something, just not right now, because a few months ago on Twitter, though, I did, I circulated a question about what are good resources. I think it was a bit more astronomy specific. And so I think, a bunch of colleagues gave me their input, and I collected it all in a Google Doc. So I have to find it. But I think perhaps that could be, maybe not the comprehensive thing, but I agree with you. Kaggle has a lot of things, but to find something which is at the right level and relevant is not easy. Duncan, is there cloud options you might use rather than student laptops, or is it a FERPA issue? Yeah, I think I could, but even for the cloud, they will need a laptop. Right? So it's true. I think all of these, they could use Google Colab. And because, in general, for like, at least for these pedagogical data sets, they are all pretty light. So I think it's enough, but some of them wouldn't have, wouldn't be able to bring a laptop to class. And every time I've tried to work in a class that has computers, then I have the opposite problems that they're like, okay, but my stuff is there. I mean, maybe I'm being, I feel like maybe because this is also my first transition, but I think maybe trying to work with something cloud-based will be the solution in future semester. I just have to plan around that a little bit more.
How do you address FERPA with Google Colab?
How do I address, sorry, what?
FERPA requirement.
Oh. I don't understand what the issue would be, but maybe I'm just not familiar.
You're giving Google student data that's private.
I know of a lot of colleagues that actually use cloud-based software in their classes. So I don't know how they do it, but I know that they do it. So I would say I understand that perhaps for if they're just running code though, right, from their Gmail account. I mean, I understand if there was grading or things like this, right? Or personal information, like if this was like an official platform, like a class management system. But I feel like just for them to be able to run some notebook, I believe it should be okay. I should definitely know. It's a good thing that you flagged this for me so I can double check with my colleagues who do it to make sure there's no other issue.
Yeah, I don't know the answer to that question. This is why I was asking. Yeah, it's their student work for the course. And there may be some flexibility. Maybe someone else can comment on that.
I'll comment real quick. So many campuses, mine included, we issue Google student accounts. And so they're actually part of the university student account is actually Google. And if they have a Google student account, it by default comes with a Colab access. So that's already handled under the university, in my case, the university's FERPA restrictions. That may not be the case if your university does not use Google for other student accounts.
I see. Yeah, does it have so they get a Gmail account?
Yeah, Google. They get a default Google account when they sign up as students.
Thanks. I'll look into that. Google's notorious for at least, and I don't know that there's a special situation for universities through Google in that sense. Yeah. Okay. I'll look into that.
We're part of the University of North Carolina system, and we have a dedicated data hub that we use. And that has served us pretty well. It doesn't release any information about the students from it, as far as I know, at least, if you believe everything we're told.
Right.
We use a self-hosted Jupyter server. We're not doing machine learning on it, but in principle you could. It's if you're just using Google Colab for basically to run Jupyter stuff, that's pretty easy to self-host.
Right, these are all good ideas. We are pretty resource limited, but I think these are things that it's good for me. Like I'm making notes and keeping it in mind in case it's something we can explore as well.
We are getting on the hour plus 4 minutes. This might be a little bit late for some people. Do we have any other questions?
Yeah, when's your next coming out?
Okay, and then me. Okay. Vivian, could you please share with us the link of the course in Concursa that you shared before, please?
Absolutely. And I can also, if I find this link to this Google Doc with additional resources, maybe I can include that as well. I will send it to you and Patricia. Is that,
yes.
Or Patricia, if I send it to you, would you be able to share it with
I can share. Yeah, I can share.
Fantastic.
Thank you so much.
Of course.
Yeah, thank you.
Thanks.
Thank you.
If we don't have more questions, that's it. Thank you so much, Viviana.
Thank you, everyone.
Thank you, Viviana.
Great to meet